this shows, and I promised this a while ago, this shows where your Taylor polynomial model actually comes from. All right? So f prime of x given f of x. All right? So my constant would go to 0. My c sub 1 x minus a. Well, c sub 1 is a constant multiple. So it would be c sub 1 times the derivative of x minus a. All right, the derivative of x minus a would just be a 1 because the c sub 1 is constant and the a is constant and x has a derivative equal to 1. All right. For the next one, you could actually kind of just power rule, chain rule it up. It's not really too much in the world of chain rule because the inner function doesn't have a derivative other than 1. So it's pretty easy to do. We'd be looking at 2 times c sub 2 times x minus a plus 3 times c sub 3 x minus a squared. Then eventually we would get to n c sub n x minus a to the n minus 1. All right. So that would be, we're going derivative term by term, but actually, as it turns out, you really only need to worry about the last term. Right? Because everything else is just power rule in, intermediate parts, but it's the last one that kind of tells you the rule of what's going on. So we have n times c to the n, c sub n, x minus a to the n minus 1. All right, so it's just power rule, mini chain rule applied here. So I'm going to take the derivative again. This time the c sub 1 is going to go to 0. All right, and so we'd be looking at 2c sub 2, because we'd pick up with this guy, plus 6 times c sub 3 times x minus a. All right. Then we would continue the journey. We would do the next one in the sequence if we had it. We don't really want to have to worry about that. So I would just write plus ... n times n minus 1 times c sub n times x minus a to the n minus 2. All right, so applying the power rule again, this n business, they're really just numerical values, so we can treat them the same way we would any other constant multiplier or power. Multiply power by coefficient, reduce the power by 1. So that's what's happening here. Now, obviously, we don't want to continue this process forever, but we'll do it one more step just to kind of get a good feel for it, hopefully. The constant part will go away. The derivative of 6c sub 3 times x minus a would be 6 times c sub 3. Then you'd have a whole bunch of other stuff. Then power rule on this guy, which would become n times n minus 1 times n minus 2 times c sub n x minus a to the n minus 3. All right, so really what we're getting at is a rule that's it's developing, it's taking shape. Huh. That's weird. Okay. I'd like to think I had a reason for why I wrote what I wrote, but something seems to be missing. All right, so f of a is telling us to replace all our x's with a's. All right, so just going back to the to the original function, we'd rewrite it as c sub o plus c sub 1 times a minus a. All right, that'll cancel. All right, plus c sub 2 times a minus a, and so on. And you notice that this zeroes out. All right. Well, it zeroes out, or at least for every part that involves an x, you would have a resulting expression here of just whatever that initial constant value was, right? Whatever your c sub o is. So, c sub o. Because everything else, again, is going to zero out because of the x minus a. So then we're going to do it for the derivative, the first derivative. All right. Here you could see, and now we just reason it out, right? Just rewrite it just to have everything cancel out again. F prime of x, everywhere I have an x minus a, it's going to zero out. So from your third term all the way down the line, everything's gone. So all we're left with is a 0 plus c sub 1. So we're looking at c sub 1. There. What's that? C sub. Here. Oh, f prime of x, where x is equal to a. Right? Yeah, whenever you're substituting into a function involving a derivative, the substitution happens after the derivative has already happened. So we're working off of this answer for this one, this answer for this one, and so on. All right. So f double prime of a. So basically, it's the first term. I mean, spoiler. So I underlined the wrong one. 2c sub 2, and then 6c sub 3. All right. So it appears, I mean, we could assume the coefficient of 1 here. It appears that there is some kind of pattern when it's the case where we're finding derivatives at a. All right. So where did the 1 come from, or where would the 1 come from? Where would the 2 come from? Where would the 6 come from? And then when we get around to it, the coefficient when you do the 4th derivative, the 10th derivative, the 20th derivative, where would those coefficients come from? All right. 1 is the same as 1 factorial. 2 is the same as 2 factorial. 3, oh, sorry, got to do a groove there. 6 is the same as 3 factorial. All right. So it does seem to be a factorial pattern where we're looking at n factorial times c sub n. All right, all dependent on whatever the level of the derivative is. All right. So I'm gonna. All right. So this polynomial is actually going to have the same characteristics that develop in the Taylor polynomial. All right. So what we need is we just kind of go back to the original expression, the original function. It was c sub o, c sub 1, c sub everything. All right. When we looked at the function itself, we had this guy here that was strictly dependent on whatever that constant value was. But now, actually, as it turns out, because generally speaking, we're going to be given a function. If we have a function, then we can make a lot of determinations about anything based off of that function, right? So having that c sub whatever there, that stuff there, is messing everything up. But now what I have is actually a relationship right here that exist between c sub whatever, in this case n, and everything else. All right. So if I solve this for c sub n, I get f to the n, so the nth derivative of f at a over n factorial. All right. So that becomes a multiplier. All right. So if you're looking at your original function, it was f of x equals a whole bunch of stuff, and then that final term, which was c sub n times x minus, well, I think we used an a up here, to the n. Now, if you follow this model, I mean, all that stuff before, it's all well and good, but it's that last term that we care about. That c we wouldn't have known. But now I know that I can replace this c with this. All right. And it doesn't look like it's helping the situation. Oh, by the way, it's not a typo, but it would be better if my constants here matched up. So, but I'll take it. And so, long story short, I'm going to take it as a typo. So if somebody wants to submit it on page 84, make it f of c instead of f of a. Actually, no. On top of 85, make it a instead of c. Because here I need it to be c because we got c all over the place if I need to. So top of 85, change c to a. I don't know what that means. I don't know. Okay. So this doesn't look like it's helpful, but it really is, because I'm given a function in terms of x, and I'm giving a center to that function. There's some place to focus my attention. The epicenter of the earthquake. That's really what's happening here. That would be the a value. Then I have everything I need, because as long as I can make a determination of how many terms I want to go out in my sequence, then I'm good to go. Right? So my derivative, how many derivatives I'm willing to go out, where I'm centering my Taylor polynomial, and n would be consistent with the number of derivatives that I'm going out. So much easier to handle here. All right. And so that actually leads us to this polynomial form, which again I have on the next page. All right. So these I'd like to be all A's moving forward. It'll look a little nicer. But